All right, pre-calculus today we're going to talk about 11.4a, which is where we start talking about limits at infinity. So consider the function f of x equals x plus 1 divided by 2x. Put that in your y1 and you graph it, and you get a graph that looks like this. So I have already actually graphed it. Ta-da! And my graph looks a lot like that one, except it's not quite as pretty because, well, I didn't use a little, I don't know. I guess I could zoom in and it'd be just as pretty. All right, so now let's take a look at what the limits are. So we're going to take a look at what the limit is as x approaches positive infinity, and then a limit as x approaches negative infinity, because these are going to be two different values. Okay, so here we're going to go to our table. Okay, and I'm going to change my table set, and I'm going to change my table value to, I don't know, 10, and we'll start at 0. All right, so table. All right, so at 0, you can see there's nothing. Okay, but as I approach positive infinity, what do my numbers stay near? It stays right around 0.5. Okay, so that's going to be 1/2. Now let's go the opposite way, and we're going to go towards negative infinity and see what happens here. Okay, so now what are we getting really close to? Well, the same thing. We're getting 0.498, 0.4986, 0.49865. Okay, we're getting really close to 0.5, which is 1/2. Remember that when we're looking at limits, we're looking at what is it getting really, really close to, not what does it actually equal. Okay. Okay. So that's a look at that. So let's actually look at the definitions for limits at infinity. Okay, so this first one says, if f is a real function and L1 and L2 are real numbers, then these statements, the limit as x approaches negative infinity for the function equals L1. And once again, that's the limit as x approaches negative infinity. And the limit as x approaches positive infinity for the function is L2. So it's going to be two different limits at infinity. That's okay because we're approaching negative infinity and positive infinity. So to note the limits at infinity, the first is read as the limit of f of x as x approaches negative infinity is L1. And the second is read the limit of f of x as x approaches infinity is L2. Okay. So the limits at infinity, if r is a positive real number, then we're going to have limit as x approaches infinity of 1 over x to the r equals 0. That's the limit towards the right. Furthermore, if x to the r is defined when x is less than 0, then we will have a limit toward the left also. Okay, so let's take a look at how we can use this and this in some actual limit problems here. Okay, so the first one, hey, don't look at this yet. Okay, so the first one says the limit of 4 minus 3 over x squared as x approaches infinity. Okay, well, let's look at this as kind of two separate pieces here. So right here, okay, our limit as x approaches infinity for this, using our rule here, from here, says that the limit of 1 over x to some real number, positive real number, is 0. Okay, so that means this is going to be equal to 0. So then our limit of 4 minus 0 as x approaches infinity is just going to be 4. Let's take a look at the next one. So this next one right here, we're going to have negative 2x plus 3 over 3x squared plus 1. Okay, so let's break that down. Okay, so that one right there. So this next one, sorry, I'm I had to sneeze, and so I paused it, so I forgot where I was at. So this one right here, the limit as for negative 2x plus 3 over 3x squared plus 1 as x approaches infinity. Well, let's look at this right here. So we talked about asymptotes a whole lot, and we know that if this is bottom heavy, that we are going to have an asymptote, a vertical asymptote at y equals 0. So we know that our limit as x approaches infinity is going to be at at 0 if we have that asymptote there. Okay. So now let's take a look at this last one. So this last one is the same. Okay. So we know that our asymptote, if these are the same, is going to be the coefficient of the top divided by the coefficient of the bottom. So that is going to be our asymptote. Okay, so we're going to start looking a lot at asymptotes for these functions here to make these, to figure out where these are at, because asymptotes, right, is where a graph approaches a certain point, but it doesn't cross it, and that's the same thing that limits are. Okay, so this right here says for the rational function f of x equals n of x over d of x, where these are just polynomials. That's all this is saying. So if we have a limit of some function as x approaches positive or negative, okay, where that function is one polynomial divided by another polynomial, we're going to have 3 different cases here. Okay, so our 3 different cases are going to be, if this thing is bottom heavy, it's going to equal 0. If the x values are the same, right? So this would be an x squared over an x squared. This one would be an x over an x squared. Okay. If this thing is the same, then it's going to be the coefficient over the other coefficient. And it is not going to exist if it is top heavy, because remember, if this thing is top heavy, there is no horizontal or no vertical asymptote. There is instead going to be a slant asymptote. Okay, so if this thing is top heavy, then it does not exist. Okay, so we're going to use those to actually start finding these limits as we progress. Now, you don't have to remember all of these rules from up here. Okay, you need to remember this stuff here. This is the important stuff. Okay, your asymptotes. Okay, you have to know asymptotes and how to find them. Okay, so bottom heavy equals 0. If they're the same, x squared over x squared, then it's the coefficient divided by the coefficient. And if it's top heavy, there is no vertical asymptote, so it does not exist. Okay. All right, so let's take a look at an example problem. So this one says you are manufacturing a product that costs 50 cents per unit to produce. Your initial investment is $5,000, which implies that the total cost for producing is this function. So your average cost per unit is the cost overall divided by however many units you make. Okay, so that is going to be our function. Okay, so it says find x at 1,000. Okay, so here, if we're looking at this, we can find what our cost of 1,000 is just by plugging 1,000 in here. Okay, so if we plug 1,000 in here, and we're not looking at limits yet, now we're just looking at the cost at $1,000, or for 1,000 units. Okay, so if we plug 1,000 in, then we get $5.50 per unit. So it costs us $5.50 to make. If we make 10,000 of these things, then it's only going to cost us $1 each to make. If we make 100,000 of these things, then it's going to cost us 55 cents each to make. Okay, and then the last one, I think it wound up on my next page somehow. Okay, and then the last one says, what is the limit as x approaches infinity? Okay, so we have here, okay, this is the same. Okay, so it's the same. So it's going to be 0.5 over 1, because those are our coefficients, 0.5x and 1x. Okay, so that means it is going to be 0.50 cents. So no matter what we do, as we make more and more of these things, it's never going to cost less than 50 cents to make. Okay, this 5,000 gets smaller and smaller and smaller because it's broken up over more and more units. But this 50 cents is standard. Okay, so it's always going to cost at least 50 cents. Okay, so as x approaches infinity, our limit is going to be, or our cost to manufacture each item is going to be 50 cents. Okay. All right, and that looks like that's all for 11.4a. I'll see you guys next time.